Hey guys, in this video we're going to be looking at binary search, so what it is, where we can find it in our everyday lives, and why it's such an effective algorithm at searching really large collections of data. Before we actually get into this though, I want you to imagine this. This is just a stack of books. Now the books in here are sorted in no particular order. They're not sorted alphabetically or anything, it's just a unsorted stack of books. So my question is, if I asked you to find a book, like find the book called X, how would you go about doing this? So one way of doing this is with a linear search. We don't actually know what order the books are in, so we'd have to go through each one by one until we find the book. In this case, we start at the top of the stack and we keep asking the question, is this X? No. Is this X? No. And we eventually get through all the books until we find the book called X, or we don't find it at all. But the idea is we're going through this one by one and comparing it to what we're looking for. And this is a linear search. But what if these books were sorted alphabetically? How would this change the way you search? Feel free to pause the video and have a think about this. If you had a giant collection of books sorted alphabetically, how would you search differently? Would you start at the beginning and go one by one, or would you do something different? Could you use the fact that the books are sorted to your advantage when searching? Well, let's say we have a sorted stack of books. So in this case, the books on the top have a lower alphabetical index, so they begin with A and B and so forth. And down the bottom, they start to approach Z. Now imagine we have instead of a stack of books, we have a lot of books lined up between two bookends like we see here. So on the left, we have books beginning with A, and on the right we have books beginning with Z. So they're sorted alphabetically, and there's a hell of a lot more books here. So over here we have books beginning with A, E is maybe somewhere here, books beginning with E are here, and books beginning with Z are at the very end. But you get the idea. This is sorted alphabetically. Now if I ask you to find the book called Lisp in Small Pieces, how would you do this? There's a lot more books than we had before. So we could go about it by using a linear search. We could go from the beginning and go one by one, but this is very slow. Imagine we had 5,000 books here. In the worst case, we have to do 5,000 comparisons. We have to look at 5,000 books to find the one that we're looking for. So how would you do this? How would you go about searching this collection? And you can stop again and think about this. Well, one way to do it, and here's one strategy, is we could look at the first letter of the book in the title and jump ahead to roughly where that would be. So we're looking for a book called Lisp in Small Pieces, so we're looking for the letter L. So here's a good educated guess. We just choose roughly here. This is probably where L is. Now let's check what book we found. We found a book called Java, A Beginner's Guide. So this begins with J. But from this point, where is L? Well, we know all the books on the left are A to J, right? And all the books to the right of this book are J, K, L, M, and so forth, all the way to Z. So what we ask here is Lisp in Small Pieces to the left or right of this point? So by looking at this, we have two portions. We have the yellow portion and the pink portion. The yellow portion is all the books beginning with A, B, C, etc., all the way up to J. And all the pink books are books beginning with letters after J, right? J, K, L, and so forth, all the way to Z. Well, books beginning with L are to the right of this book. The book we're looking for, Lisp in Small Pieces, must be in this portion if it is in here. And that means we can just disregard this portion on the left because we know it's not in there. So we don't have to search that. We've now reduced our search space to this portion on the right. These are the books we're going to search. So we continue searching in this section. So we make another guess and we say, okay, maybe L is here this time. And we were wrong again. So this is M. Okay, this is MATLAB, an exercise book. And we do the same process. What we do is we say, what letters come before this one, and where would the book be? Lisp in Small Pieces. Where would it be in relation to this point? Well, the portion on the right wouldn't contain L because that's all the letters after M, and L comes before M. So it must be here in the left portion, right? And that's what we're doing. At each book we pull out, we're asking, where would this be? Does it lie on the left or the right of where we're looking at? So now what we've done is we've disregarded that portion on the right. So if Lisp in Small Pieces is in here, it must be in these three books. But now we only ever have to search 3 books. So we've cut down our search space dramatically. And this is the idea behind a binary search. It's kind of like a binary search. It's not exactly the same, and we'll talk about that soon, but it employs the same principles, using the fact that it's sorted data to our advantage and narrowing the search space until we find what we want. The fundamental part of this is we look at something within the data and ask, is what we're trying to find to the left or to the right of this point? And this is exactly the same notion as in binary search. A good example of where we do this kind of search is with dictionaries. Now, dictionaries contain thousands and thousands of words, but we can generally find the word we're looking for in barely any time at all. This is because dictionaries are ordered, and we use that fact to our advantage. We search them by flicking roughly to where the word would be, and we reduce our search space dramatically because of that. Now, imagine if a dictionary was unordered. Imagine how useless that would be as a document. If you look for a particular word, you'd have to go through each one by one until you eventually reach what you're looking for. So the next question is, how is binary search different? We talked about a solution, but we did say, it's kind of like a binary search. So what is the difference? Well, we do the same comparison process and refine our search space, but we don't guess willy-nilly. We go directly into the middle of the search space and use this as a comparison. So we split it in two each time. And to give you a better idea of this, here is an ordered list of numbers ranging from 0 to 52. And as you can see, they're sorted from smallest to largest. So the smallest on the left, largest on the right. So say we're looking for 5 in this list. How would we do this with binary search? Well, instead of guessing, we cut the current search space in two. So you can imagine this as a line. So draw a line in between the middle, and you ask, is 5 to the left of this line or is it to the right? It's very similar to what we did with the books. So what we're doing is we're saying, is 5 to the left of this line or to the right? Well, this is between 10 and 11, right? So 5 is to the left of this. We disregard this portion on the right, and we keep doing this process in the search space on the left. So we do this again. We split that in two, and we ask, is 5 to the left of this? Is it between 5 and 6? We've got the line between 5 and 6. We're saying, is it to the left of this line? Well, it is, in fact, again, on the left. So we do the same thing. We cut that portion in half, and we ask, is 5 to the left or right at this point? It's to the right in this case. So we cut out that portion, and we do the same with these last two elements. We say, is 5 on the right or is 5 on the left? And 5's on the right. So we found what we were looking for. And you might ask, why is this called binary search? It's got nothing to do with ones and zeros. Well, we call it binary search because at every comparison, we can make two choices. We either choose the left or the right. We're cutting the search space in two each time, and this is why it's called a binary search. Now, binary search is really good at searching very big collections of data, and this is its main use. Maybe using binary search for 5 items is a bit overkill, but it really comes into play when we have massive collections of data. So to give you an example, here is 1,296 items in a list. As you can see, it's a lot of data. On the first comparison with binary search, we immediately cut that search space in half. Now we're only looking at 648 items. And then we do it again. We keep cutting it in half again and again and again and again and again and again until finally we're left with the thing that we wanted to find. So we only did 10 comparisons there to find the thing we're looking for out of 1,296. This is the same speed as searching for something with linear search that is 10 items in length. That is ridiculously fast. So just to contrast these two algorithms, here is how many comparisons linear search would have took to find the same item. So 542 comparisons. We would have to start at the beginning, checking each one until we reach the 542nd item, and that would be the one we're looking for. With binary search, however, we only did this 10 times. So that is 5,420% more comparisons. The best thing about binary search is it scales well. So the more data you have, the more data that can be eliminated from each comparison. It scales very well, and it's very good for big collections of data. So thanks for listening, and if you're interested in other computing topics, please check out the videos on this channel. Thank you.